I'm going to give some notes on, we're done with types of bonding so far. We're going to carry this into intermolecular forces, which in your book would be chapter 16. So intermolecular forces are those forces that hold your molecules together, not your atoms together to make your molecule, but your molecules together to make solids, liquids, and gases and have specific properties. Intermolecular, between molecules. So intramolecular forces are the ones you've been dealing with. They're the ones that give you the tetrahedral or the trigonal pyramidal structure. That structure is what is going to determine these intermolecular forces. You're looking at the shape of your molecule and its polarity, and then how the molecules are held together. That will determine the strength of their bonds, whether they are solids at room temperature, liquids, gases, a lot of their physical properties. So, in keeping the term straight, interstate goes between states, and intermolecular goes between molecules. Again, the intra are within. These are your covalent bonds. These are much, much stronger than your intermolecular forces. Water, for an example, here's the intermolecular force that holds water together, the attraction of hydrogen for one water molecule for the oxygen of the other. When we boil water, that's the force that we break. We do not break the hydrogen away from the oxygen. That would be a chemical change. So your intermolecular forces are all of your phase changes that we're looking at. So all of your intermolecular forces depend on your intramolecular forces, which determine your structure. So once you know the structure, you can determine the intermolecular force. It's really that simple. And all you're looking at with this structure is whether the molecule is polar or not. So when you did your homework before I posted the key, you may have had some difficulty determining that polarity. It really would have helped, of course, to be able to build with the molecules. Some people don't need to. They can look at the little molecules they made with their toothpicks, or they can use the computer program and they understand whether the molecule is symmetrical or not. So you have to be able to determine polarity in order to determine intermolecular forces. So the physical properties are going to depend on these: boiling point, freezing point, melting point, solubility, volatility. So determine the intermolecular forces, we just need to determine the polarity. Now, in order to determine the polarity, we had to build the molecule correctly. In order to do that, we had to draw a correct Lewis dot structure. In order to do that, we had to know the rules. So it all goes back to building up to this point. So it's not just a matter of saying, oh, okay, well, I didn't need to know all of that. I can just look at the polarity. Well, you could if we give you a molecule that's already drawn, but chances are you're going to have to do that yourself. So let's look at all of the types of bonding, because that's what we're looking at in this unit. We know that ionic compounds are cations and anions, transfer of electrons, strong electrostatic forces of attraction, strong bonds, high melting points. The way that they're held together is with ion-ion forces or ionic bonding. It's one of the strongest. Now, if you move forward in chemistry, there are things with stronger bonds, diamond and quartz and other things like that. But right now, for this level of chemistry, your ionic compounds are the strongest that you will encounter. Again, they're made by a transfer of electrons, completely opposite forces with strong bonds. Because of those strong bonds, they are brittle. If you push on a compound that has strong attractive forces and you force like charges over, then the crystal will break.
Sodium chloride is typical of ionic solids. The crystal contains alternating sodium cations and chloride anions packed in a three-dimensional array. Ionic solids are brittle if deformed and will fracture along planes of packed ions.
So that's it for properties, physical properties of ionic compounds right now. So they're all solids at room temperature. So if you were to look at a crystalline substance, you couldn't for sure know because sugar is a solid at room temperature and it's not an ionic compound. So you would have to test things like their melting points and other things, which would have been a lab we would have done in class. We would have had several unlabeled compounds and we would have tested their properties. Now let's move into molecular compounds. These are your covalently bonded compounds, two or more non-metal elements bonded with a sharing of electrons. So if you have a covalent compound, here you've got two nonmetals sharing a pair of electrons. The electronegativity differences between these two atoms that are bonded will result in a polar bond or a bond dipole. Now, if you have a simple molecule that's just two atoms and you have a bond that is polar, then the molecule will be polar. So the partial positive end of one molecule will be attracted to the partial negative end of the other. These forces are called dipole-dipole forces. If you have a polar molecule, this is the type of attractive force that exists. It is not as strong as ionic. These are not a transfer of electrons. They're just a partial end of the molecule that's positive being attracted to the partial end of the other molecule that's negative. It is a permanent attraction, but it is not nearly as strong as ionic. This symbol means partial. So dipole-dipole, and the term is pretty straightforward. You're looking at a molecule that has two poles, a positive end and a negative end, and it's attracted to another molecule by its positive end and negative end. And they arrange themselves so that these attractive forces are strengthened. So it's a permanent dipole, a permanent polarity, and the opposite ends of the dipole attract each other so the molecules can stay close together. So molecules that attract each other by dipole-dipole are often liquids, sometimes very soft solids, but they're not brittle solids with strong bonds like ionic. So once you drew your Lewis dot structure and you saw that you had a polar molecule, you would say that they were attracted to each other by dipole-dipole forces. That's it. And dipole-dipole forces are weaker than ionic.
Bonds between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules, such as sulfur dioxide, are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
So that's it. As long as you have a polar molecule, you have a dipole-dipole force of attraction between the molecules. So your polar molecules have dipole-dipole intermolecular forces. We often abbreviate intermolecular forces IMF. These are moderate intermolecular forces. They're not as strong as ionic. You can have solids, but they will be soft solids or they will be liquids. This is not water in here, but whatever liquid this is probably dipole-dipole. Hydrogen bonding is a special kind of dipole-dipole. This occurs when you have hydrogen. So you have to have hydrogen within your molecule. And it has to be covalently bonded to either fluorine or nitrogen or oxygen. So in order to hydrogen bond within the molecule, the covalent bond has to have hydrogen covalently bonded to one of these three highly electronegative elements. Then, just like dipole-dipole, the positive end, the hydrogen, is going to be attracted to the negative end, which would be the nitrogen, oxygen, or fluorine on the other molecule. So the hydrogen of one water molecule is attracted to the oxygen on the other. The reason it is particularly strong is that the hydrogen atom is incredibly small compared to other atoms, and we're talking about a very electronegative element, nitrogen, oxygen, or fluorine, on the molecule that it's going to be attracted to. So you just get a particularly strong intermolecular force. If you think back to Coulomb's law, you can get the hydrogen much closer to the oxygen, and you have a greater difference in charge, so you have a much stronger bond. It's a dipole-dipole, two polar molecules, but it's unique in its strength, and it is called hydrogen bonding. It is the strongest kind of dipole-dipole, so it's given a unique name. So the small size of hydrogen and the large electronegativity of these three elements will give you this incredibly strong bonding. This is not your hydrogen bond. This, the bond between, and I hate using the term bond because it's still just an intermolecular force. It's not a covalent bond, but it's been historically called hydrogen bonding. It is the hydrogen on one molecule attracted to what has to be nitrogen, oxygen, or fluorine on the other molecule.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with two hydrogen atoms and two unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So the electronegative atoms are oxygen, and fluorine and nitrogen. Those are the only three that can form that hydrogen bond. Finally, you get to your weakest intermolecular forces. So if you have nonpolar molecules, well, they also can exert forces on each other. Otherwise, they would be all gases. There would be no nonpolar molecules that weren't gases. Remember, your properties of gases is that they do not exert attractive forces. So nonpolar molecules do exert forces, but they're very weak. The way they exert their forces is that at some point in time, the electrons become disrupted. They are no longer evenly distributed. So if you get that disruption in the electron cloud, it gives you an instantaneous dipole or an instantaneous polarity. So all of a sudden, you have this simple electron cloud where everything is shared equally, and your electrons are going around each nucleus, and then all of a sudden the electron cloud gets disrupted so that you get a partial positive and negative end. What that does is then causes a polarity in the molecule next to it. It induces a dipole in the molecule next to it, and for that short instant of time, they are attracted to each other. Now, these are not permanent polarities, unlike your dipole-dipole, where they were only partial charges, they were permanent attractions. These are instantaneous and induced, and they last for a very short period of time, but they do last long enough to hold substances in the liquid and sometimes the solid state. So induced dipole-dipole. Typically, we call those London dispersion forces, and we abbreviate it LDF. So here you've got two hydrogen molecules, both nonpolar, not attracting each other. There's no positive or negative end, but all of a sudden the electron cloud gets distorted because you never know at any given time. The electrons are 90% of the time where we expect them to be, but 10% of the time they are wherever they want to be. So for a short period of time, there's a polarity that induces a polarity. So the negative end causes a positive end of this molecule, and then there's a short attraction, but then it goes away, and the polarities of the molecules go away. And then they come back and they induce a dipole, and then there's an attraction, and then it goes away. But these London dispersion forces, okay, can last. If you cool down substances, these forces can last longer. If you have really large molecules and you have more of these distortions of the electron clouds, then you can get solid states from them. So every single substance has London dispersion forces. Dipole, dipole, ionic, everything has this disruption in the electron cloud. It's just with a nonpolar molecule, it's the only thing holding them together. So for nonpolar molecules, you have only LDF forces. Everything else has LDF forces, but they have stronger forces as well: hydrogen bonding, dipole, dipole, and ionic. The bigger your molecule, the more electrons you would have, so the more disruptions you would get. We call that polarizability. So if your molecule is larger and it is more polarizable, then you will have more of these London dispersion forces and stronger overall intermolecular forces. These are much weaker than all of the other intermolecular forces. They're weak, they are not permanent, they are short-lived. You can get them to last longer at cold temperatures. So you can get liquid hydrogen. It's normally a gas at room temperature, but if you cool it down and you get these forces to last longer, then you can form hydrogen in the solid state.
In solid carbon dioxide, dry ice, nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So, nonpolar molecules have London dispersion forces. They would be gases. Okay. Wax is a nonpolar molecule, but it's got a very low melting point. So we know that it's got London dispersion forces because of its low melting point and its weak intermolecular forces. So your ionic at one end is strongest, and your LDF forces, London dispersion, at the other end are the weakest. Then you've got your polar. So here's your nonpolar molecule. So that's flat out, if it's nonpolar, LDF. If it's a metal and a nonmetal, it's ionic. And then you have your polar compounds that are covalently bonded. And you've got your hydrogen bonding, which is quite unique. You've got hydrogen bonded to nitrogen, oxygen, or fluorine, and that is a stronger bond than your regular polar dipole-dipole. Now, within these, you can get some overlap, okay? But it's important to remember that the relative strengths of these determine the melting points and boiling points. But we know that water is hydrogen bonding. It's a hydrogen bonding molecule. Bonds to itself with those strong, special dipole-dipole forces. But it's still just a liquid. And wax, which has a formula of C25H52, is a straight chain nonpolar molecule. It's just a huge molecule. So even though it's nonpolar with weak London dispersion forces, they have so many of those London dispersion forces that it actually is stronger than the hydrogen bonding. So there's always a chance that you will get some overlap. But at the level you're working, if you can simply predict on the basis of the strength of those, you should be okay. So if you see a solid that you know we know this has a transition metal in it because it's a colored solid, so we know that, and it's also crystalline, we know that that's ionic. If you have a solid or a liquid, a soft solid, you are going to probably predict dipole-dipole. You don't know for sure, but you're certainly not going to predict that gummy bears are ionic. Within your dipole-dipole, you do have the unique hydrogen bonding where you have covalently bonded hydrogen. So you don't want to get carried away and think that hydrogen bonding is stronger than everything. It's not. Okay? So the gummy bears are made out of sugar. Sugar is a polar molecule, and it can hydrogen bond as well, but it's got a lot of other dipole-dipole forces in it. And then you've got your weakest London dispersion forces, so you're looking at primarily the gas state or very soft solids. So let's look at some examples. So here are your types of intermolecular forces. So if we looked at xenon, it's a noble gas, it's an element, it's not attached to itself at all, it's a gas at room temperature. So since it is a nonpolar, we're going to call that London dispersion forces. All of your noble gases are held together by London dispersion forces. They're all nonpolar. HCl is a simple polar molecule. It cannot hydrogen bond. If you drew its Lewis dot structure, try to draw it out without getting too sloppy here. It's just polar. I'm not going to put the lone pairs of electrons on all of them, but chlorine is not electronegative enough to allow for hydrogen bonding, but it is polar, so it is dipole-dipole. HF, hydrogen fluoride, does have the ability to hydrogen bond. So if you were comparing these two, HF would have a stronger intermolecular force than HCl. Its boiling point would be higher and so on. Calcium chloride, think about what that would be, what criteria. Pretty quickly you should recognize that's ionic. Again, it's an ionic compound, metal, nonmetal. CH4, now just looking at it, if you're really good, you know that CH4 is a tetrahedral molecule, you've built it, and it is quite symmetrical, so it is nonpolar. So if it's a nonpolar molecule, look at your choices. It's going to be LDF. Carbon monoxide, a very simple molecule, two different atoms. So therefore, if you've got a linear molecule with just two different atoms, it is polar. So it can't hydrogen bond, so it's just dipole-dipole. Ammonia. If you drew ammonia out, which you have done, you're going to get a trigonal pyramidal structure with a lone pair of electrons on the nitrogen. Trigonal pyramidal's always polar. So you might go with dipole-dipole, but if you stop and look, those hydrogens are covalently bonded to nitrogens, so ammonia is a hydrogen bonding intermolecular force. NO would be dipole-dipole because it's a polar molecule, and BF3 is a nonpolar molecule. Remember, boron likes to have only 3 pairs of electrons, so it has that trigonal planar, which is 120-degree bond angles, nonpolar, so it's going to be London dispersion forces. So you're trying to decide between these two molecules which one has the strongest bonding. So if you want to test yourself, you should pause right now and go through and see if you can decide between Br2 and I2 which one. So what you're looking for first is one polar and the other not, because if one is polar, that's dipole-dipole, which should be stronger than LDF. Can one of them hydrogen bond while the other can't? Okay, so pause the video if you want to try this yourself. If you're looking at Br2 and I2, they're both simple nonpolar molecules, so they're both London dispersion forces. But iodine is much larger, has much more, many more electrons in its structure. Look at it on the periodic table. It's down from bromine. So if you have more electrons, so if you have the same type of bonding in something, then you have to look a little deeper. What is it about them? And it will always come down in the end to which one has more electrons and greater London dispersion forces. So let's look at NH3 and NCl3. They're both polar, no doubt about it. So how are you going to decide? Well, if you remember, ammonia can hydrogen bond. So NCl3 would have dipole-dipole, but the hydrogen bonding of ammonia is stronger than just the dipole-dipole. Here you've got a polar ammonia and a nonpolar. So there's a much greater strength of bond in the polar molecule. And of course, we just said ammonia can also hydrogen bond. So to do these, you're going to need to either be really good at remembering your structure, or you're going to have to draw your Lewis dot structures. If you draw the Lewis dot structure for methane, it's completely nonpolar, and PCl3 has a lone pair of electrons. So this is tetrahedral and this is trigonal pyramidal. Remember, this all comes down to polarity. So PCl3 is dipole-dipole, which is stronger than the LDF. Up here, you've got an ionic compound. Ammonia can hydrogen bond. Now you've got two molecules that if you built them would be nonpolar. But C2H6 is much larger. So if they're both nonpolar and have only London dispersion, the larger molecule will have stronger London dispersion forces because it has more electrons, more chances for disruption of those electrons, and more of those instantaneous attractions. And down at the bottom, water can hydrogen bond, but calcium hydroxide is ionic. So you can pause yourself on these and make your own decisions. Okay. This looks like a crystalline structure to me. I know it happens to be, let me go back to where I was. I know it happens to be copper 2 sulfate, so it is an ionic compound. Ammonia can hydrogen bond. This structure, you really do have to know what the colors of the atoms are. These are 2 carbons, and these are hydrogens and oxygens. The red are oxygens. So notice that the hydrogen is attached to an oxygen. So this molecule can hydrogen bond to another molecule like it. The hydrogen on this molecule would attach to the oxygen on either of these oxygens. So this molecule can undergo hydrogen bonding as its intermolecular force. This molecule is nonpolar. Nonpolar molecules, London dispersion forces. LDF, nonpolar. HCl is a polar molecule. It can't hydrogen bond, so it's just good old dipole-dipole. Well, snowman is made out of water. Water is H2O. H2O can hydrogen bond. If somebody gave you SO3, if you can't draw the Lewis dot structure, then chances are you're not going to get this right. When you draw the Lewis dot structure, you can see that it's trigonal planar. Trigonal planar is nonpolar. It is London dispersion forces are the type of intermolecular force. Wax, if you don't know the formula, you might say, well, it could be dipole-dipole because it is solid, but wax is a hydrocarbon. It's composed of just carbon and hydrogen. Any molecule composed of just those 2 elements has only London dispersion forces. It's just a very large molecule, C25H52, 25 carbons, 52 hydrogens, makes it highly polarizable so that those London dispersion forces are very strong. Here you have a crystalline substance. If you know and have seen, and some of you have, when you made salt in the laboratory, some of you tasted it and some of you put it under the stereoscope. This is an ionic compound. This is sodium chloride. So SF6, structure is octahedral. Octahedral, as long as there are no lone pairs or different atoms, would have London dispersion forces because it is nonpolar. This is oil. Oil is highly nonpolar. Doesn't mix with water. That's how you know it's nonpolar. And if it's nonpolar, it's London dispersion forces. SO2 is a bent molecule, and it's got those 2 lone pairs of electrons. If it's bent, it's polar, it's dipole-dipole. It cannot hydrogen bond, but it is polar. This would be metallic bonding, metals. Carbon tetrachloride, nonpolar LDF. CO2, nonpolar. Those lone pairs of electrons on the end don't have anything to do with that overall structure being nonpolar. The dipoles cancel in CO2 and London dispersion forces. That explains why it is a gas at room temperature. It's got weak intermolecular forces. Hydrogen fluoride, you might be tempted to go just to dipole-dipole because it's polar, but it can hydrogen bond because of the hydrogen attached to the highly electronegative fluorine. So what intermolecular forces are present in C2H4? Well, if you draw C2H4 out, you will see that it is nonpolar, so therefore London dispersion forces only. What is the dominant intermolecular force in HF? The dominant is hydrogen bonding. It also, has dipole-dipole forces because it's polar, but it has the particularly strong dipole-dipole forces of hydrogen bonding. And then we said all molecules have London dispersion. So all three of these are present in HF. It's the hydrogen bonding, though, that gives it its strength of bonding and is the dominant intermolecular force. Which of the following substances has the strongest intermolecular force? Well, let's look at this. Radon is a non-polar noble gas. Chlorine is a non-polar, Cl2. So those are both London dispersion forces. H2S is polar, so that would be dipole-dipole, and NO is polar, so that would be dipole-dipole. CH3, though, can hydrogen bond. Here's the part of the molecule where you have a nitrogen and you've got some hydrogens coming off of it. So the nitrogen would have hydrogens coming off. And for these lone pairs on the nitrogen, the hydrogen on one molecule would be strongly attracted to the nitrogen on the other. So this is your answer because of its ability to hydrogen bond. So polarity is what's going to allow you to separate molecules from each other in chromatography. So chromatography is separating a physical mixture of two or more compounds by distributing those compounds between two phases, a stationary phase and a mobile phase. And I can't believe you would not have done some chromatography up till now, certainly in honors biology. You may have done some chromatography of plant pigments. So it's based on the structure of your molecules, so they're mixed together, and based on the difference in their structure, you're going to be able to separate them. The polarity of those structures is what you're really looking at. The polarity determines whether or not you're attracted to the stationary or the mobile phase, and that allows you to be separated. So if a substance is more attracted to the mobile phase, then it's going to travel up the chromatography paper faster than a substance that is more attracted to the stationary phase. They need to be attracted to both. So if they were only attracted to the mobile phase, they would all rise up the chromatography paper and go off the top of it. And if they're only attracted to the stationary phase, they wouldn't move at all. So they need to be attracted to both to varying degrees. So it's really their structure and eventually their polarity that will allow them to be separated. So your stationary phase is for paper chromatography, a piece of paper. So you are going to do a kitchen chromatography lab, and you can be fairly creative with this. You can use paper towels, you can use coffee filters, or any other porous paper. It's pretty difficult to use your white typing paper because it's got a coating on it, but any other paper is fine. Your mobile phase is going to be water or a mixture of other substance if you choose. When you place your paper into your mobile phase, you want to make sure that your chromatography line or dot, you can do lines or dots, is below the surface of that liquid. Otherwise, it will just wash off. But over time, the dyes are attracted in differing degrees, okay, to the mobile or stationary phase as they rise up. So this dye, black ink, separated into the yellow, the red, and the blue. So if you were looking, you could see that the blue was more attracted to the mobile phase because it rose higher on the paper, while the yellow stayed more attracted in general to the stationary phase, based on their different polarities and how they're attracted. Now, you don't know for sure the polarities of your mobile and stationary phase. I will say, for the most part, your mobile phase will be your polar and your stationary phase will be your non-polar, typically phase. Not always the case, but for your paper chromatography, that usually is the case. So here, a student did a separation, okay, of dyes in fruit drinks. So first they had the pure colors that they put down on the chromatography paper, and you can see that their green pigment separated into yellow and blue, okay. Their red definitely had several different colors. Their blue was sort of a blue and red. So which of these pigments was more attracted to the mobile phase? Well, the one that rose higher on the paper. So if the mobile phase is polar, then the blue dye is more polar than the yellow dye. If the paper is nonpolar, then the nonpolar substances are attracted more to the paper and don't rise as high. And that was the case in this scenario. So here's how you're going to do your chromatography. You're going to cut a paper towel, maybe a coffee filter, or hunt around your house for some other type of paper. You're going to make a pencil mark several centimeters from the bottom and put some tick marks on it, and then label whatever you're testing. So you can test markers. So if you're testing markers, you want to apply several layers of the color, let it absorb in. You can do this with toothpicks if you're doing food coloring, or if you're doing soft drinks that have color, you can pull the color out of any of the things you can find around your house. Marker pens are just pretty easy to use. You want to make sure you're not using permanent pens. So here they spotted colors, and then they put down black ink. And we know that black ink is a mixture of other pigments. So now you're going to take that and you're going to put it into your water solvent. So you want to make sure that you notice that the bottom did not touch. So let's pause this a minute. So the way I think they have this, it looks like they've got two toothpicks that are kind of stuck to the beaker with clay. It looked like they kind of slid their plate in between. You can also just put a pencil across the top and attach it with some tape. It needs to touch the liquid, but you cannot let the liquid touch the spots directly. So you want the liquid to just touch. If you set the paper and it sets down, it's not attached to anything, and it's just sitting in the liquid, it often will bend under and fall down. So you really do need to support it by taping it, or I like the way that they have the little toothpicks there, but that looks a little more difficult. But you do need to have it supported so that you can watch the pigments rise up. Let me get out of my pen here, go to my arrow so I can start this up again. So you'll see that the ink will begin to rise up on the paper. Then you want to cover it. Any cover will do. The paper needs to have water vapor, okay, as well as just the liquid. So we really want a saturated environment, so covering it really does help that. And these can take some time, and we don't want it to evaporate. So with time, it will rise up the paper. You can see the separation of the pigments. Once it gets a few centimeters from the top, you can go ahead and take it out. By then, most of the pigments will have resolved. That means they have separated as much as they're going to separate. Here we see that the black ink had a mixture of the blue and the red dye. So they had the dyes here. Your yellow was a pure dye. So let's go back down. Okay. So spot your plate, and maybe when you did chromatography in biology, you drew a line and let the line rise up. That's fine. That's really lower level chromatography, depending on what you were looking at. Sometimes it's the chlorophyll. They'll usually just take a leaf and scratch the chlorophyll line, so that's fine. But it's really nice to do it with dots. So you can use food colorings, you can use drink mixes, you can even extract. You could go out and get flowers and extract the dye out of them and run chromatography. I'll give you some examples in a lab that you're going to do. So you can do any colors that you want. Okay? You want to make several thicknesses of that color, and you don't want to make the spot too big, but you do want several thicknesses so it's nice and concentrated. And then this is what we would have done in class. So you can see the dyes rising up. We actually used some fluorescent dyes that we looked at later under ultraviolet light. You can see what I'm talking about, the paper kind of sinking and bending there. You really don't want that to happen if you can help it. Okay. So let me go back a minute. I think we missed one. Yes, I want you to see this video. For some reason, I did not run it. So if you put your dots and put them directly into the solvent, then you're not going to get a result at all. They're just going to wash off. So make sure that you're really careful that you won't do that more than once. So make sure that you can see here that the solvent is below that level. So once you see all of the colors resolved, now you can do this or not. This next thing that we would do would be to calculate the RF value, which you may have also done in biology. That's the ratio to front. So we certainly can tell these were our standard pigments. This one looks contaminated. And these were our two unknowns. So you can see that unknown number 1 certainly appears to contain the known F, and unknown 2 appears to contain quite a few things, certainly E, and maybe even some F. So in order to figure out what is actually in them, we calculate the RF value, ratio to front. And you don't have to do this with your chromatogram. I just want you to experiment and see if you can separate some pigments. But what you do is, instead of just saying, well, look, I can see that unknown number 1 has the same yellow dye because they rose to the same height. So that means if I'm using the same solvent, that I'm always going to travel a fixed distance if I have a same solvent and paper. But we calculate it mathematically by measuring the distance that the spot travels over the distance that the solvent travels. And we get what's called an RF value. So the distance that the spot travels in centimeters divided by the distance that the solvent front travels. So to get the solvent front, you actually have to take your paper out of the solvent, and while it's still wet, draw that line. So feel free to do the RF value if you really want to prove what pigments are in your dyes. So let me go back before I talk about the crystal lab. So all I want you to do is to play around and separate some pigments. The lab sheet that you have access to lets you gives you some suggestions of your marker pens. If you want to try permanent marker pens, you're going to need to use some alcohol, either rubbing alcohol from the drugstore or vodka mixed with water. You can separate permanent ink with those. You can also mix water and alcohol together to separate both polar and nonpolar substances, and you can mix them in all kinds of ratios to see if you get a better separation. You can go out and take your flower petals and extract the dyes out of them, and it tells you how to do that. It's a simple boiling to get the pigments out, and then you can see if the dyes are pure or what they're composed of. So the crystal lab is perfectly optional. It's fun, and I've given you directions on how to do it, but you can also find many, many directions. I love growing crystals, and we do it for several weeks. We just watch them for weeks, and some people get some incredibly beautiful crystals. These are all student-grown crystals, and I've shown you some. The ones that are going to be the easiest for you to grow are going to be the alum crystals, which are clear, but you can grow the copper sulfate crystals as well. You would have to have, you can get alum at the grocery store, which is why it's simple. Copper sulfate, you've got to go to, I would think, any hardware store, any place where they're selling plant mixtures. Copper sulfate is used as an anti-fungicide, so you can probably find it there. But the alum crystals are fun to grow, and they grow very quickly. So sometimes they grow as a conglomerate. So why are we doing crystals? Well, because we just learned about intermolecular forces, and ionic bonding is an intermolecular force. So it's fun to kind of explore that. The crystals will grow kind of like a stop sign shape at first, and then if you suspend them in the liquid, they will grow into an octahedral, like a little diamond. To grow a perfect crystal, you have to watch them every day and break off the little crystals that are glomming onto them. If you don't want to do that, you just let them grow on each other, and they look quite pretty. The copper sulfate crystals, the copper sulfate is a skin and eye irritant, so if you get it, if you do happen to find an access to it, just make sure that you don't have younger brothers and sisters that are going to eat either one of these chemicals. So here you can see the student has grown the crystal. It started from a very small one, and now it's growing around the thread. We often have students that grow them so big that the thread breaks because the crystal gets so heavy. Alum, which you can find in the grocery store under the spices, it's a pickling salt. Its actual name is potassium aluminum sulfate. So it grows a nice clear crystal. They're not all beautiful, okay? But when they first grow, you get a bunch of little babies in the bottom, and you can follow the directions on the lab sheet I gave you, but you can Google many others. The one that I gave you is one that I have used for students in the classroom. So once you pick out the one you like the most, then you're going to tie string around it and you're going to support it in a solution so that it grows. Now, if you really want to grow this thing, you might want to tie some pretty strong string or even fishing line. Fishing line is nice because it's clear and you can't see it once the crystal grows around it. So you'll simply attach your little baby and you'll support it in solution. Now, this solution needs to be concentrated or else your crystal will dissolve. And it needs to be cool or else your crystal will dissolve. So the directions for making crystals, you've got to make sure when you make that next solution that it's concentrated more than the crystal is. Otherwise, the crystal will go into solution. So if the next day your baby is smaller, you need to take it out and make sure your solution is more concentrated and then put it back in there. So it's a matter of then once this crystal gets bigger, you take it out, you make a more concentrated solution, you put it back in, and it just gets bigger and bigger and bigger and bigger. So the pure crystal will not be cloudy, it will be more clear. Okay, that one is a pretty nice one. So the crystals are optional, but I've given you directions just to allow you to have fun. But you do, in your assignment, you do have directions on how to do chromatography, so you have to do some kind of chromatography. It doesn't have to be fancy. You've got lots of different papers you can use and lots of different dyes, but I'd like to see you try some experimentation with different pigments and different solvents. You can use water by itself or water mixed with rubbing alcohol, or if your parents have some alcohol. You don't want to use colored alcohols because they will leave, although you could separate the pigments out of the colored alcohols. But again, don't go stealing alcohol out of your parents' cabinet. You can ask if they have some clear alcohol that you can mix with water. It makes a very good solvent for some of your plant dyes. So good luck to you, and we'll talk about all of this and go over our results when we meet together on that Monday. Or Tuesday for us is our Zoom meeting, that's right.